I got all their symbols memorized and know how to name compounds. Yep. Because we're going to get into a topic called stoichiometry. And without those previous skills, this could become a nightmare. So I wasn't kidding when I wanted you to learn those things, because I knew you'd need them very quickly. Okay, stoichiometry. Up to this point, we've learned the alphabet. We've learned how to write the words, names of compounds. Now we're going to put sentences together. That is, chemical equations, to learn how to balance them. And that comes under the topic of chemical stoichiometry, which is it's a German word, I think, which just means counting. How do you count things? You remember when Lavoisier proposed the conservation of mass in a chemical reaction? Yeah, the mass of reactants equals the mass of products. Well, at that time, they didn't know why. But now we do know why. We know why because the number of elements, the number of atoms of each element on the reactant side is exactly equal to the number of elements, atoms on the product side. And that's why we count them. We count them because we've already learned hard lessons through the early 19th century that you cannot follow the progress of a reaction by mass alone. Did I tell you the story of the Karlsruhe Congress in southern Bavaria? Don't remember that? In the early and mid 1800s, chemists, this was primarily in Europe, chemists at colleges and universities and chemists working for companies, and they were actually the ones that are at greater risk, had run into a roadblock, a problem. They knew how to put chemical reactions together by mass, but when something went wrong, they had no way to fix it because mass is not the answer to how a chemical reaction progresses. So they decided to meet at Karlsruhe University in southern Bavaria. And they decided that they were going to meet there and they're going to figure this thing out. So they invited speakers, and they had a bunch of speakers come, and they tried, and they had committees, and they tried to figure out what was wrong. And they essentially threw up their hands. They couldn't figure it out, except for one talker, one paper, one scientist from Italy. His name was Cannizzaro. He was a student of Avogadro. Remember Avogadro's law? We do Avogadro's law yet? No? Okay, we will. Anyway, he proposed that reactions should be tracked and followed by the number of atoms of elements, or the number, some counting way of tracking the elements from the reactant side to the product side. And he based his work upon Avogadro's work. So he gave his talk, and then he handed out reprints of his paper. He had published a paper on this topic. And apparently some of them hadn't read it, but they did take it politely. They took his paper and they went back to their colleges and universities and companies. And some of them read the paper, and the light bulbs started going on all over Europe. They finally had a handle on how to track a reaction and correct mistakes, correct problems. That's the short version. And they did it by stoichiometry. Now, of course, the measurements that you make for a reaction can occur in several different ways. Masses are the most convenient. You can do volumes, but those have to mean something in terms of counting. So that's the relationship that we have to establish between those measurable quantities and the things that we can't see. like counting atoms. We can't see the atoms, but we develop, a good chemist develops an intuition for what is meant when he or she establishes a chemical reaction and then looks for products. So the first problem is when we weigh something, how do we make the transition from weight to numbers? Right? And that comes under a general subheading of dimensional analysis. And we've done some of that already, where you do unit conversions. That's what the dimensional analysis exercises were for, to get you ready for this. So when we say counting by weighing, think of it this way. If you have a jar of, say, marbles, and for the time being, right, it doesn't matter whether they're, I don't know what kind of marbles. I forget. I hadn't played marbles since I was a kid. I remember cat's eyes and Aggies. It doesn't matter that. What we have to assume is that all these marbles are essentially the same mass, or at least they have an average mass that we can rely on. Okay, if they have an average mass, then we take, if we get the total mass of all these, total mass in, say, grams, and then we know that each marble has an average mass of some value, then that would be so many grams per marble. So we're going to have X mass, and then our unit conversion would say so many grams per marble. And notice I inverted it because I want grams to cancel. So this is the average mass of each marble. And we could say, I don't know, Y grams per marble. Well, the grams cancel, and you're left with a calculation that tells you how many marbles are in that container. That's how we count by weighing. The key is knowing how much each one of those marbles weighs. What's its mass? Okay. The next problem is atoms are too small to weigh one at a time, right? Especially when this method was being established. And atoms, we can't count individual atoms, or at least we couldn't. We can now, but it would be very tedious to count individual atoms, and very expensive too, because you need some pretty high-priced equipment to do it. And that statement, objects, we have to assume that they all behave identically. And that's in terms, for our argument here, that's in terms of their mass. Each one has essentially the same mass. And we do that by averaging. So how would we get the average mass? Well, instead of taking the whole bottle and empty it out in their balance, let's take a representative sample, just like 10 of them. And say 10 of them have, say, 100 grams per 10 marbles. Right? So each marble then would weigh 10 grams, right? 10 grams per marble. And that's what we would put here. Okay, that's how you determine an average mass. You take a representative sample. So that also brings up, reminds us that every measurement has error. So the best way to get an accurate value here is to do this several times, over and over and over again. Take a 10 marble sample, weigh it, then throw them back in there, mix them up, take 10 more, do it again. Do it several times and get an average, and that gets you closer to the true value. It doesn't eliminate error, but it minimizes error. Okay, so here's an example where we have a pile of marbles that weigh 394.8 grams. Right, we don't know how many marbles are in there. So we want an average mass for the marbles, and we take 10 out, and they weigh 37.6 grams. So that means each marble weighs 3.760 grams per marble. And we do the calculation and find out, our calculation says there should be 105 marbles in that jar. Now, if we take them all out and count them, we can find out how close we were to the true value and do an error calculation if you want. Okay. So how do we do this for atoms when atoms are too small to weigh? Well, we have to establish a standard mass for at least one isotope, because we know different isotopes have different masses. So we have to establish a standard mass, for one of the isotopes in that periodic table. And then we can compare everything else to that one. So the one we pick as our standard is going to have infinite number of significant figures. Whatever value we pick, it has value 0.000 infinite. And then everything else is compared to that. Okay. And we use Avogadro's law for comparison purposes. Maybe I better describe that right now. We're going to get it again when we get into gases. We haven't got to gases yet, have we? No. Okay. I'm gonna describe Avogadro's law simply because talking about it extracted, standing back and talking about it doesn't make any sense to you. You need to understand what the law says. This is the pictorial version of Avogadro's law. When Avogadro was active, in fact, he didn't actually publish the law. It was published by another chemist, Gay-Lussac. But Gay-Lussac gave Avogadro credit because Gay-Lussac was working, doing his experiments based upon Avogadro's letters and communications. So he gave Avogadro credit for it. So Avogadro said that if you have two gases, swap markers, two gases in these spherical containers, imagine they're three-dimensional. They're equal volumes. Okay. And we've got a gas in here and a gas in here. So we have a gas in there and a gas in there. Doesn't matter what the gases are. That's the nice thing about gases. Under conditions that we're going to be working with them, a gas is a gas is a gas, at least for physical measurements. Okay, so you got these two gases in here, and they're both at the same temperature also. All right? Same volume, same temperature, same pressure. We can measure the pressure inside that container, and they're exactly equal. Each of these is equal. Avogadro said that if that's true, then the number of atoms, the number of molecules, the number of particles, whatever they happen to be, between the two are exactly equal. So these could be this could be hydrogen. This could be argon, for all we know. They would have exactly the same number of particles of each. Hydrogen molecules in this one, argon molecules in that one. But the masses will not necessarily be the same unless both of the gases are exactly the same. If we had hydrogen in both of them, masses would be the same because they have the same number of particles of the same molecule. But if they're different, we've got argon atoms in this one and hydrogen atoms in this one, their masses will be different. And the reason they're different is because each individual particle is a different mass than the other one. For argument's sake, this would be 2.02 units, atomic mass units. And this one would be about 40 atomic mass units. Okay. So this one's going to weigh 20 times as much as that one. That difference allows us to compare the masses of individual atoms and molecules. Because now we know if we've got equal numbers, then the difference between the two is based upon the difference between this atom and that atom. That's how Avogadro solved the problem of counting numbers of atoms. Now all we have to do is establish a standard. And then we can put a standard in one and an unknown in the other and start comparing. Okay. So the standard we eventually settled on was the carbon-12 isotope, right? It has 6 protons. It has a mass number of 12. That means it has 6 neutrons, right? That isotope itself is, that atom of the isotope is 12.000 atomic mass units for that atom. Okay? And everything else is compared to that. Now, there are other isotopes of carbon. Well, those isotopes compared to this one are never going to be infinite zeros. They're going to be fractional numbers of something. We can say, compare this one, that isotope, it's going to be 13 point something. I don't know what. It'll be a number, and it'll have a certain number of significant figures required, depending on your measurement. Or you can have, if you can do it quick enough, carbon-14 is radioactive, so you better be quick about your measurement, or it'll be gone. It'll decay. Okay, so that's our standard, carbon-12, and your book uses just a U for atomic mass units. I like to use AMU because in the sciences, U can stand for a number of different things. It can stand for electrical potential, voltage, as an example. So I like to use AMU to be sure that we don't make a mistake. All right, we compare everything else to these. Now, getting this into the gaseous state is a little difficult. So the comparison has to be done maybe not by this way exactly, by some other methods that have been developed. But this was the Kickstarter for comparing masses of individual atoms. Originally, oxygen was used because it was more commonly available in and used in chemical reactions. But it proved to be more difficult to handle. So eventually we settled on carbon-12. You need a spectrometer, a mass spectrometer to separate the isotopes. So that takes an investment. But carbon itself is available everywhere. You can get your hands on it anywhere. All you have to do is just pyrolyze any living sample and you're going to get carbon. And then you can separate it with your mass spectrometer and do the comparison. If you have enough money and expertise. Okay. What we find on the periodic table, though, these numbers here on this periodic table are atomic mass, not mass number. Mass numbers are all whole numbers because they're protons plus neutrons. But mass numbers are weighted average of the isotopes for each of the elements. So once we find out for each of the isotopes what their mass is relative to carbon, then we have to take their relative abundance into account. It's kind of like calculating your grade point average. Right? A course that's got 3 credit hours would carry a whole lot more weight if you make an A in that course than if you have a 1 credit hour course and you make an A in that one. Okay, so we do a similar thing for calculating these values. What we need to know is what's the relative abundance of each one of the isotopes. Carbon-12 is 98.89% last time it was determined. And people do this, I mean, their whole careers are nothing but these calculations. So every 10 years or so, they recalculate them and give us a new periodic table with adjustments. But for our purposes, the adjustments are usually in the 6th or 7th or 8th decimal point. So if we restrict ourselves to 2 decimal points, it doesn't matter how old the periodic table is. We're good to go. Okay. Other isotope, the other stable isotope is only 1%. So it's going to contribute less of its atomic mass units to the total than carbon-12 is. And then carbon-14 is negligible. So we could do an example calculation with just the 2 carbon isotopes, 12 and 13, and get an idea of how this value was arrived at. I'm sorry, I ended a sentence with a preposition. My English teacher's rolling over in her grave. So what you want to do is say, what is the contribution of 12 atomic mass units from carbon-12? And its decimal point equivalent to percent is the way I like to work it, is 0.9889. So it's that fraction of 12 that contributes to the total. Okay. And then the determined mass units for 13 are 13.0034 because it's compared to 12. And it only contributes 0.0111 fraction. So if you multiply the fraction times the atomic mass units and then add them up, you should get a value of about 12.01. And that's 2 decimal places on the periodic table. That's where that value comes from. I did it again. Okay. Now, here's a good question. If I were able to isolate an individual atom, just at random, from a sample of carbon, we know it's pure carbon, but it has a mixture of isotopes, the 13s, the 14s, the 12s. I think there's even 11, but most of the others are radioactive and in negligible amounts. But if I had that sample and I reached in there and I was able to grab one of those, right? What's the chance that that one would have a mass of 12.01? You know, probability. Zero. No probability. It would not, none of them would have 12.01 because it's a weighted average of the total. There's nothing in there. No one of those atoms has exactly 12.01. We take that average mass because it's convenient. When we're working in the lab, we don't have time to deal with isotopes. We're dealing with natural samples. So people that have time and equipment, they determine what the average mass is for us. Then when we make our calculations in the lab, we can use that value because we're using a sample of naturally occurring mixture of those isotopes. So 12.01 is a weighted average, not representative of any isotope. That was my point. All right. This is just an artist's rendition of how we separate the isotopes. This is actually, it's a specific type of mass spectrometer called a magnetic sector. The magnetic sector is there in the middle of the picture. So we know that if you fire an ion through a magnetic field, it's going to bend. Now, the problem with that picture is they've got it bending toward one of the magnets. Ions don't do that. When ions pass through a magnetic field, they bend right angles to the field. Right? So they're taking liberties. Anyway, what you have to do is turn the sample into a gas, which is what we do at first. We heat it up until it turns into a gas. And all this is done under vacuum. And then you run it through a grid that strips off the electrons and gives you positive ions. Usually you only have to strip off one electron and that's enough. You set your device so that's all it does. That simplifies your calculations later. Then you accelerate it through an electric field. That positive ion is accelerated toward the first plate is negatively charged. Second plate is negatively charged. And the only ones that make it through are the ones that are going straight. That's a collimated beam. When you can send a stream of particles through two openings that are lined up, then you know your beam is straight. Then you send it through your magnetic sector, and the ones that bend the most, they all have the same kinetic energy, right? Because they're accelerated through the same magnet, through the same electric field. But the ones with the greater mass have the lower velocity. Kinetic energy. Kinetic energy of any particle is determined by its mass and the square of its velocity. So what that says is the more massive ones are traveling slower because they're inversely proportional. So the more massive ones are traveling slower, the force on them is due to their charge, right, in the magnetic field. So they all feel the same force, but the heavier ones bend less. So they're going to end up on this end of the detector, and the lighter ones are going to bend more. That's how you differentiate them. Now that's one type. We've got several different types of mass spectrometers, and these are very expensive, and they have their value, right? They're very accurate, very fine resolution, but sometimes you don't need that, and you can make a cheaper one with, there's one that I used to use with my gas, it was attached to my gas spectrometer, my gas chromatograph. It had a spectrometer on the end, and it was not this design. It was called a quadrupole, which is neither here nor there, but just to let you know there are differences. Okay. So let's clear the board. All right. So for this example, we have an element consists of 62.6% of one isotope, and its mass is 186,956 atomic mass units. And then another isotope, these are the two most common. So we're going to restrict ourselves to these two isotopes, 37.4% with a mass of 184.953. What's the average atomic mass, and identify the element? Okay, let's do the atomic mass first. So 186.956. 56 atomic mass units. And what it contributes to the average, the weighted average, is 0.6260. 0.6260. Notice I use the fraction. The other one is 184,953. It's a little bit lighter, and it's less abundant, 3740. Okay, so that's what they contribute, and then we just add them together. So the first one, 186.956 and 0.6260 contributes 117, let's see, four significant figures. 117.0. That's its contribution to the average. The other one, 184.93 times 0.374 is 69.17, four significant figures. Okay, Now, when we add them together, we get a 7, a 1, 6, 16, 8, 186. And if we're going to be comply with, right, we're limited to that one right there. So we have 186.2 atomic mass units is the average. Okay. Now, how do we find out which element that is? We've already learned that if you know the atomic number, you know the number of protons, you know the element. No mistake. I mean, there's no possibility for error there. But finding the number of protons is not the easiest thing to do. Atomic mass, yeah, well, that's easy. So what we notice from the periodic table is not only do the atomic numbers increase from left to right, top to bottom, the masses also increase from left to right, top to bottom. Now, there's chance for some overlap because we're taking weighted averages, but you can usually get pretty close. 186.2, so we just follow. Look at these numbers. 186.2. It looks like the closest one to that one is rhenium. I didn't have you memorize that one. That's how you spell it out. It's R-H-E-N-I. Okay. And we'll have problems like that in the future, right? Identify the element. Just all you know is the mass. Now, occasionally you'll have some that are very close together. And I was looking to see, they might be within experimental error sometimes. Tellurium and iodine are pretty close, 127.6 and 126.9. They're really close. Selenium, bromine are close. There's some others in the table that are close. So if they're within your experimental error, then you've got to have another way to determine, break the tie. But most of the time, this is almost as definitive as atomic number. All right. So up to this point, we've been talking about individual atoms, collections of individual atoms of the elements, the isotopes, and what that means for the mass of each atom. But we don't have any balances that measure individual atoms. And we can't count individual atoms. So what we came up with was a unit that was large enough so that we could weigh them on our laboratory balances. So what we need, because each atom is very small, right? So we need a large number of those atoms so that we can put them on our balance and weigh them. And we need to have that number defined so that when we weigh something on our balance, we can relate that to this large number. And that large number is called the mole. That's the way you write the whole word. And then when you abbreviate it, you drop the E. Makes a lot of sense, right? Somebody decided the mole is a very, very large number. Okay. It could be atoms, like it could be a carbon-12 isotope atoms. It could be molecules, like our diatomic elements, like dihydrogen, nitrogen, oxygen, fluorine, chlorine. It could be a mole of those. It could be a mole of bigger molecules, like glucose, C6H12O6. Could be a mole of those. It's just a number. Now, it is tied to reality. This number is refined over time, and it's based upon actual laboratory experiments and measurements. Okay. And the reason that I can say that is because of what this number represents. Up to this point, that's the atomic mass units average for that element and all its isotopes, naturally occurring isotopes. But if we have a mole of those isotopes, say bromine is, no, chlorine is better, 3545. We say that an individual weighted average of chlorine is 3545 atomic mass units. But if we have a mole of those, 1 mole of chlorine, we have 35.45 grams. Those numbers are interchangeable. If you have a mole, you've got that many grams. If you only have 1 atom, then your weighted average is the value you go with. That's where the mole is significant. Because if you have a mole, you have that many grams. Or if you weigh that many grams, you know you have a mole. Okay. It's based upon carbon-12. What we're saying is that a mole of carbon-12 is equal to exactly 12 grams. That's an exact number. No limit to its significant figures. All right. And we call that Avogadro's number in honor of his theory that established, made it possible for us to actually measure that value. And of course, if you have naturally occurring carbon, then you're going to have a mixture of isotopes, and a mole of those would be 12.01 grams. So when we actually calculate masses of moles of compounds, where we add up the individual elements, then we're going to use these values, not the ideal value for each isotope. Okay. All right. So let's see, what do you do with that? That's where you really learn chemistry, is you solve problems. So what if we want to know how many iron atoms we have in 4.48 moles of iron? Okay. Here's dimensional analysis. Remember, I said a lot of problems in chemistry can be solved purely by dimensional analysis. We want to change that moles into grams. We need a conversion factor with moles on the bottom, so that it'll cancel here, grams on the top. Whenever you see, we know we need that conversion factor to give us our answer. So whenever you see the need for grams and moles in a quotient relationship, think molar mass. So we look for iron, and iron is 5585 to two decimal places. When I say 85, yeah, like that. Now that's the hard part. We've done all the thinking. Now we just crunch numbers. And I get, let's see, I wonder if they're going to be standard notation or scientific notation. Scientific notation would be 3 decimal places, and the second, or 250 grams. One or the other should show up in the answer. Oops. Oh, wait a minute. How many atoms? You guys didn't correct me. Well, that's how many grams it would be. All right, let's solve it the way it was supposed to be solved. If we have moles of iron and we want atoms, what we need is atoms. And we know that one atom, 6.022 times 10 to the 23rd atoms per mole. Moles cancel. And that gives us our answer. Times 24 atoms. But so that I don't waste the effort, that many atoms of iron weighs 250 grams. Trying to make lemonade. Okay, let's see. Got another one. Mass in grams of 1 mole of a substance. Molar mass, that's what we mean by molar mass. Now, you'll often see me slip into the way I originally learned it as a student, molecular weight. But molar mass is the proper term. Molar mass just means how much does a mole of this substance weigh? So molar mass of nitrogen is this, mass in grams of 1 mole of substance, okay? We can read it off the periodic table if it's just an element. But if it's a molecule, like water, if you have 1 mole of water molecules, how many moles of oxygen do you have? For each mole of this, you have 1 mole of oxygen, correct? Yeah. So you have 1 mole of oxygen. How many moles of hydrogen do you have? 2. You have 2 moles of hydrogen. So 1 mole of oxygen on average is 16 grams per mole. 2 moles of hydrogen is 2 times 1.01 grams per mole, or 2.02 grams per mole. Actually, this is per mole of water. This is per mole of water, because we took 2 into account. All right, so now that we have per mole of water, we just add 16 plus 2.02, and we get 18.02 grams per mole of water. That's how you do the molar mass for compounds. You just add up the molar mass for all the atoms or the elements in the compound times how many there are for each one. Okay, there's water. Here's a bigger one. Barium nitrate. Let's see, did we write this correctly? Nitrate is a polyatomic ion with a -1 charge, correct? Barium is a huge alkaline earth with a 2+ charge. So we do need 2 of these, don't we? That's how you write the compound. Now, to do the calculation, if we have 1 mole of this compound, then we have 1 mole of barium at 137.33. 137.33 grams per mole. We have how many nitrogens? We have 2 nitrogens. Right, because of that. 2 nitrogens. So we have 2 times 14.01 for nitrogen. Same units of measure. How about oxygens? We have 6 oxygens. And each oxygen to 2 decimal places is 16. So you say 137.33 plus 28.02 plus 96, right? And you should end up at 261.35 grams per mole of the formula. That formula. So if you have 1 mole of this, it should weigh 261 grams. All right. I don't know why I keep this slide in here, because if you get a question like this on exam, it's simple, quick and dirty. You don't have to do calculation. Which of the following is closest to the average mass of one atom of copper? There's no copper atom that weighs 63.55 grams, right? That would be huge copper atom, right? The only one that makes sense is E. And we can calculate it. Let me see if I animated. Yeah. Okay, so there's the calculation that gives you that value. But you can reason it out and end up with that value. Okay, and all we did was dimensional analysis. One copper atom, how many moles of copper? We have to get moles of copper because that's our only bridge to mass. We got to get moles to go to mass. So that's why we had to convert the copper atom to how many moles. It's a small fraction of a mole. And then so many grams per mole times that fraction makes a very small value. How about the number of copper atoms in 63.55 gram sample of copper? This is kind of a trick question. If you look at the mass of copper on your periodic table, 63.55 grams per mole, you've got a mole of atoms, or 6.022 times 10 to the 23rd. Okay. Is this twisting anybody's brains around yet? Okay. All right. So let's say we have 100 gram samples of each one of these elements. So this is one of the methods that I use to solve problems, especially when you have multiple calculations that are going to be the same form for each one. So I call it invoking Henry Ford. An assembly line. Set up an assembly line for each one. Magnesium, zinc, and silver. Magnesium, zinc, and silver. We've got 100 grams of each one. 4 significant figures. See, so we're doing the same thing for each one with slight changes to accommodate each of the elements. Which has the greatest number of atoms? Now, do we need to go all the way down to the number of atoms? No, we just need to go to where we can count. And we can go down to moles, and that'll tell us. We can count, put things in order, which one has the greatest number. So with 100 grams, all we need to do is convert each one of these, cancel the grams, leave us with moles. Once we know moles, then we can compare numbers. So how about magnesium? Now let's look on the table. 24.31. And that's to 2 decimal places. I rounded to 2. Zinc. There's zinc right there. 30. 65.38. Okay. And silver is a heavy one. 107.87. That. Now remember, these are exact numbers. These are the ones that determine significant figures. So we can have 4 significant figures in our answer. There's Henry Ford. We're doing the same thing for each one and then comparing the results. So if we take 100 and divide by 24.31, I get 4 significant figures. 114. 4.114 moles. Do the same thing for 65.38. And we got 1.530 moles. And then 100 divided by 107.87 be less than 1. 0.9270 moles. This is magnesium. This is zinc. This is, oops. Let's do zinc again. Silver. Okay. Which one has the greatest number of atoms? The one with the greatest number of moles. This one right here. Okay. We have the same mass for each one. Why are they different? Because silver weighs more for each atom. So it has fewer numbers of atoms required to make 100 grams. This is the least, this is the middle, and that's the most. Okay. Now, I went to a lot of trouble to do that calculation, but since we have the exact same mass for each one, I didn't have to go that far, really. On an exam, all you need to do is, if that's the case, all you need is the difference between these. The heaviest one's going to be the fewest number of atoms. The lightest one's going to be the most. So rather than do all that calculation, I could have said, that's magnesium. Okay. But what if you got different masses? Now you have to either do the exact calculation or estimate. And to answer the question, order from greatest to least, all we have to do is estimate the number of moles of each one. So for magnesium, we're starting off with 21.0, right? 21.0 grams. All right, that's C. We changed the order. So I left it in this order and I'm just picking the information out of the question. Zinc is 70. Yeah, 70 grams. And silver is 107.9, 107.9 grams. Okay. When we divide this into that, you get about 1, don't you? 1 mole. Right. 107 and 107 and 1. 65 and a 70 is what? It's greater than 1 mole. And 24 into 21 is less than 1 mole, because the denominator is bigger than the numerator. Now we can put them in order from greatest to least. Okay, greatest, zinc. Greatest to least numbers, zinc, and then the middle is silver, and then magnesium. There we go. Zinc, silver, magnesium. So I've sort of introduced test-taking techniques here too. You know, get you through that question quick. Move on. All right. This one is in serious need of Henry Ford. I don't know if Henry Ford invented the assembly line or if he just made it profitable. I mean his rampant anti-Semitism and racial bigotry aside, he did know how to run a company. Okay, if we have 100 gram samples of each of these, rank them from greatest to least number of oxygen atoms. Okay, this takes it one step further. So if we set up our assembly line here, because we got lab to work with today. If we set these up in order of, give ourselves lots of room. Water's the first one, and then nitrogen monoxide and C3H6O2, which we haven't learned to name yet. It's an organic compound. I suspect that's propionic acid. And then CO2. Carbon dioxide. Water, dihydrogen monoxide. Back Several decades ago, there was this thing floating around on the internet. And it was cautioning people about the hazards of dihydrogen monoxide. Since most people don't know how to name compounds, they thought that was a strange chemical. It was water. Okay, we got 100 grams of each. All right. So we start our assembly line here. All right. If we're going to convert to numbers, if we had to order these and put them in the order of numbers of oxygen atoms, we got to find out the numbers of molecules first. Then we can make a conversion to oxygen atoms. So the conversion has to go from grams to moles first. Moles of compound. We need the molar mass of each one. We did water earlier, if you recall. 18.02 grams. N2O, so we need two nitrogens, 14.01, which is 28.02, right? Two of them, and 16 for oxygen, 44.02. There. Okay. This one take a little more work. 3 carbons, 3 times 12.01, 6 hydrogens, 1.01. This is grams per mole. And 2 times oxygens. There we go. So I'm not going to rely on my almost 72-year-old brain. 6 and 32. 7409 is the molar mass of that compound. And carbon dioxide. Well, let's see. Carbon is 12.01 and 2 times 16 is 32. That's 104. 4401. Almost the same as dinitrogen monoxide. The common name for that is laughing gas. That's nitrous oxide. Okay, so I think the first time I do this, I better do this calculation and then extend it to the next calculation. But you could set it up to do one calculation all the way through. This tells us moles of compound, right? Or do you want to do it? You want to do it through in one calculation? We've already calculated cancel grams, left us with moles of compound. Maybe I will do it that way. This way we only have to do one calculation, then it reduces the risk of rounding errors. Now we want to get rid of compound and oxygen. Moles of compound, moles of oxygen. I left out the mole part. Okay. So this allows us to cancel moles of compound and leave us with moles of oxygen. So what's the ratio? What's the conversion factor here? Well, how many moles of oxygen per mole of compound? And this one is 1 to 1, right? So for every one, you got 1. This one, for every mole of compound, you got 1 of oxygen. This one, you got 2 oxygen for every mole of compound. And this one, you have 2 oxygen for every mole of compound. Okay? So now we've done all our thinking, we can crunch numbers. 100. 18.02 divide and times 1. So it's 5.55. Now for 4 significant figures. So let's do 5.549 moles of oxygen in 100 grams of water. The next one. Let's see, 44.02 divide there, and again, 1. So this one is 2.272 moles of oxygen. And we go back to 100. Divide by 74.09 and multiply times 2. This one is 2.699 moles of oxygen in 100 grams of that compound. And then back to 100. Let's see. 44.01 times 2 is 4.544 moles oxygen. Okay. Now it wants to put us in order from greatest to least. Let's see, this is the least, right? So that'd be number 1. This would be number 2. This would be 3. This would be 4. Greatest. Oh, greatest to least. I'm sorry, I got it backwards. This would be 1. This would be 2. Did I do that right? That's right. 1, 2, 3, and 4. Yeah. Water's first, then carbon dioxide, then propionic acid, then laughing gas. For the number of moles of oxygen, or the number of oxygen atoms, right, in that order. Okay, problem solving. We've been doing that up to now. The first thing you do when you're presented with a problem, well, you read it, of course, but after you read it, what's the question? What does the problem expect you to determine as the answer? If you can't get past that one, then throw up your hands and walk out. If you can't find the question, then you'll never get the answer. And then you devise a strategy based upon your training, what you know, to get that answer. And in that process, you look for information in the problem as given. Does it have everything you need to solve the problem based upon the structure of the solution that you've developed? If it doesn't, then you might have to go outside the problem and get information, like usually go to the periodic table or go to your useful information and find conversion factors or formulas that are given in your useful information. And then once you've got your answer, ask yourself, does it make sense? Is it reasonable? I had a friend in when I was at LSU. I was in the agronomy department, which is crops and soils, and he was in mechanical engineering department, and we were neighbors in the apartment complex. And we talked a lot, and he told me about some of the students in the class with him. Said they had such a bad tunnel vision that you come to an exam and the instructor would give them a question, and they would think only in terms of the chapter they had just studied. And they took the information, the numbers given in the problem, and pigeonholed them into formulas and things they developed in that chapter only. And they come out with some outrageous numbers like, I don't know, the weight of a grain of sand is 43 million tons, or something like that. And it wouldn't faze them that their answer made no sense. Right? They didn't do that last step. Does your answer make sense? And I imagine that mechanical engineering is cumulative science, just like chemistry. The stuff you learn in the previous chapters, you better hang on to it because you might need it. Okay. So one of the ways that we determine the composition of a compound and express it is in percent mass. Mass percent of each element in the compound. And that simply means that if you have 100 grams of the compound and the mass percent is 20, then that 100 grams will have 20% of that element in the compound. That's all that means. It's really simple. There are two ways to get that value. If you have the formula for the compound, you can calculate that value. And I'll show you that in a minute. The other way is the way bench chemists do it. You have a compound, an unknown compound, and you're either told or you have to determine what elements are in that compound. Then you need to go to a technique that will allow you to quantify the amount of each element in that sample. And then you can calculate mass percent. The mass of the element you determined divided by the mass of the compound that went into that determination times 100. And that's your percent composition. And that's the first step. If you have an unknown compound, that's the first step in determining what is the molecular formula of that compound. Okay, here's the way you do it if you have a formula and you want to calculate the mass percent. You act as if Fe2O3, right? That would be iron 3 oxide, is the name of that compound. If you want to determine the mass percent of each element in that formula, what you need is, say, you have to nail down one corner. You say you have 1 mole of the compound. If I have 1 mole of that compound, what mass do I have? Well, you need 2 times iron, which is 5585. And you have 3 oxygens at 16 each. Okay. Starting to get a little weak. 55.85 times 2 is 111.7 grams. And then 3 times 16 is 48. Oops, I went the wrong direction. 55, I had to start over again. And then there we go. So this is 159.7. Yeah, I want to keep decimal points to avoid rounding errors. This is how many grams per mole. So for 1 mole, the mass of the compound would be 159.70 grams. How much of that mass, if you only got 1 mole, how much of that mass is due to the iron? It's this amount. $111.7 grams. 111.70 grams. That's iron. This is the compound times 100. So I get, I'm going to round it off, 69.9% iron. Okay. If you have the formula, that's how you calculate mass percent. And we can do the same thing for oxygen. You can either go through all this mess, or you can say, right, if we got 2 elements, one element is 69.9%, what's the other element? It's 30.06 or 30.1. This is percent oxygen, right? Because they have to add up to 100%. So yeah, that gives us 100. Or you can do it the hard way. Okay. I should have kept all that stuff up on the board. Because we were almost there. Okay. We want to go to all that trouble. What if we just do one of them? To give you a feel. Highest to lowest percent oxygen by mass. Maybe we better do it. Yeah, we go. So do I have another? Yeah, I've got another one in here. Okay, so we're back to H2O, dinitrogen monoxide, propionic acid, and CO2. Okay, if we want to calculate percent by mass, that's okay. This is fine. If we've got 100 grams of each one, that's what I call blue smoke. Because answering the question, you don't need to know the mass. I mean, you could, but it's easier just to do the molar mass of each of the compounds, put that in the denominator, then put the mass of each of the oxygens in the numerator and do the calculation, right? Instead of doing 100 grams and trying to figure out, all right, what mass of this 100 grams is due to oxygen. That's going to take a number of steps. So it's easier just to throw that out and go to what we know. So in the denominator, we're going to have the total here is 18.02 grams per mole. One oxygen is 16 times 100. There you go. That'll give you water. This one is 16 again for oxygen, but 16 plus 28.02 is 44.02 times 100. Okay. This one is 2 times 16 is 32. So 32 grams are present in a mole of that compound. 32 plus 6.06 for the hydrogens, right? 6 times 1.01 and 3 times 12.01. 3063, 3603. That's 9014 and 7409 times 100. And then carbon dioxide is 12.01 plus 32 for the oxygen. Goes up here. And that's 4401. Okay. And then we can do the calculations. I can't do those in my head and do an order, so we'll just have to calculate them out. Highest to lowest percent oxygen. So 16 divided by 18.02 is 88.8% oxygen by mass. So we should say, instead of that, we should say mass. That says mass in the numerator, mass in the denominator. Oxygen. And then 16 divided by 44.02, it's going to be less, is 36.3 oxygen. And then 32 divided by 74.09 is 43.2%. And then last but not least, 4.01 is 72.7. Okay. We put them in order by percent oxygen. Water's number highest to lowest. Water's 1, CO2 is 2. This one's 3. There's 4. There you go. Okay. Henry Ford strikes again. Boy, those things don't last very long. The only advantage to buying my own is when I get, let's see, what are those they give us? They buy Expo. Expo is good, but they're a bear to erase. These guys erase real easy. So that's why I like my own. Okay, so that takes care of that problem. Now that we know how to express composition in terms of mass, which makes sense because mass is one of the easiest things to measure in the lab. The next thing we want to do is to calculate or determine the molecular formula. What is the actual ratio of moles of atoms in the formula? Right? If we're talking about benzene, which is a 6-ring structure, and each one of these in organic chemistry, when you have 2 lines coming together, that's a carbon. And then we don't write the hydrogens in there either, but there are always 4 bonds. So if we do it like that, there's 1, 2, 3 here, there has to be a hydrogen there. So each one of these has a hydrogen attached to those carbons. But if we write that formula, there's 1, 2, 3, 4, 5, 6 carbons and 6 hydrogens. Right? So that's benzene. If we take acetylene is a triple bond carbon with a hydrogen on each end, right? And anybody who's ever run a cutting torch knows acetylene. But this is 2 to 2, C2H2, right? They're different formulas for the molecule, each of these molecules. But if we express them in their simplest whole number ratio, what's the ratio? For every 1 carbon, there's 1 hydrogen, correct? For every 1 carbon, there's 1 hydrogen. So this is what we call the empirical formula. For either of these is CH. Okay? These are the molecular formulas. When we go to the bench and determine the percent composition by mass, we can take that information and find this value. So it could be the same for either one of these. And that happens a lot. But that's our first step. If we need to go from here to here, we need to know the actual molar mass of the compound. The molar mass of this compound is going to be less than that one, obviously, because this has 3 times as many atoms as that one does. So that's where we're headed. We're going to use percent by mass to determine the empirical formula. And then if we're given the molar mass of the compound, we can take that information and go the next step to the molecular formula. All right. This is an example of how you would determine carbon, hydrogen, and oxygen in a carbohydrate. Everybody knows what carbs are, right? Like simple sugars, starches, they're all carbohydrates, which means they only have carbon, hydrogen, and oxygen in them. That's it, nothing else. If you know that for a fact, then you can use this technique, and I've done this in the lab. You can take your sample and put it in a furnace, which is that black thing around there. Put your sample in the furnace and blow oxygen over it, and it causes it to oxidize. All right, it burns. And it produces, if it's complete combustion, it produces water and carbon dioxide as a product. And the oxygen then you determine by difference. So you can take the water tells you how much hydrogen was in the compound. Carbon dioxide tells you how much carbon is in the compound. And then you know the mass of the compound that you put in there. So the difference in that is due to oxygen. You can't do the oxygen directly, right? Because you're blowing a ton of it through already. So we use, to absorb water, we use magnesium perchlorate, which works great. It's a good water absorber. And then we get the CO2 from sodium hydroxide. Okay, we scrub out the CO2 with sodium hydroxide, and it produces sodium carbonate as your product. And you simply take those things apart, you weigh them before and after. You know what's going to cause the difference, and that gives you a value for the water and the carbon dioxide. Okay, so here's our first example. And the first calculation we're going to learn how to do is the empirical formula, which again is the simplest whole number ratio of elements in the formula. Okay. And then we're going to take the information that's given there, the molar mass of the compound, to go the next step. So first we have to do the empirical formula. Henry Ford again, 49.3% carbon. Carbon, 49.3% by mass, 6.9% hydrogen. Oops, getting out of order here. Hydrogen, 6.9%, and then oxygen is 43.8%. 8%. And when you work these problems, there's a method to doing it. So learn the steps. When you're given percent by mass, if I haven't said before, percent is a dimensionless number. It simply means parts per 100 parts. That's what percent means. But we know that these parts are grams per 100 grams. Right? We can't convert percent into moles of anything, right? Because it's not mass. So what we have to do is assume we have a 100-gram sample. If we have 100 grams of the sample, then we have 49.3 grams of carbon and 6.9 grams of hydrogen and 43.8 grams of oxygen. That should add up to 100. Now, according to the law of definite composition, that this ratio is fixed for that compound. No matter how we get it, that compound is going to have the same ratio. So the ratio by mass is fixed. What we need to do is determine the ratio by moles in order to write the formula. Because the formula is not written in mass, it's written in moles. Numbers of atoms, moles of atoms in the compound. So now we need to convert these to moles. And since the ratio is fixed, when we convert to moles, that ratio is fixed also. Got to get rid of the grams and leave us with moles. There it is, moles over grams, molar mass. So carbon is 12.01, hydrogen is 1.01. You can find this on the periodic table. Oxygen is 16 to 2 decimal places. This gives us the ratio of moles of carbon, hydrogen, and oxygen. So 49.3 divided by 12.01 is 4.10. 4.10 moles of carbon. 6.9 divided by 1.01 is 6.83. Hydrogen. And oxygen is 43.8 grams divided by 16 is 2.74. Okay. What's wrong with this picture? Those are not whole number ratios. So what we have to do, this ratio is fixed. So anything we do to one, if we do it to the other one, then we haven't changed the ratio. Say we multiply by a number, or we divide by a number. I wouldn't add or subtract. That would mess things up. But multiply or divide, and the ratio is still the same. Well, the simplest way to deal with it is to take the smallest one and divide everything through by the smallest value. So we're going to divide by 2.74. Okay. This is obviously 1. Then 6.83 divided by 2.74 is about 2.5. At this point, really close is good enough. It was actually 2.493, but 2.5 is close enough. I mean, it's within experimental error. And then 4.10 divided by 2.74 is about 1.5. So I probably should do this. That. Somebody new? Oh, there's Jacob. Okay. Well, you're only in the lab, Jacob, so unless you have a question, we're not going to do anything in the lab today. We're still not a whole number, but we're close. Okay. So how can we make each one of these whole numbers? How do you get rid of a half of a number? Multiply by 2, right? Because this would be, what? 1.5 is like 3 halves, isn't it? 3 halves times 2 would be 3. So times 2 would be 3. Times 2 would be 5. And times 2 would be 2. Now we got our whole number ratio. So our empirical formula is C2H5O3. C3H5O2. That's our empirical formula. What's the molecular formula relationship to the empirical? There's a whole number multiple. Like C2H2 for acetylene, if we multiply by 3, we get C6H6. So what I'm saying is, if we multiply each one of these by the same number, then we'll get our molecular formula. Because the ratio must stay the same. We multiply each one of these by the same number, then the ratio is the same, but we also get the molecular formula versus the empirical formula. So how do you do that? Well, I do it by empirical weight, or the molar mass of the empirical formula is what? Well, 3 times 12.01 for carbon is 36.03. And then 5.05 for the hydrogens, and then 32 for the oxygens. That's 73.08. 73.08 grams per mole of the formula. Okay? Now, if N equals 1, then the empirical formula and the molecular formula are identical. And the molecular formula should have exactly the same weight, right? Because it's the same formula. Right? 73.08. Well, we were given 146. 146 point, that's it, grams per mole. That's the molar mass of the formula. The molecular formula. Right? So that's not it. What if N equals 2? What's 2 times 73? 146. So if N equals 2, we got that value because we've doubled everything in here times that. So our molecular formula should be C6H10O4. right? And if you want to check it, just add up, do the molar mass for that compound, you'll get that value. Okay, I gave it to you that way as a logical expression, but as a practical matter, if you're given this type of problem in the future, calculate this value, take this value, divide by this value, and it's about 2, and that's equal to that value. Okay. Either way works. So let's see, they should give us the answer. C3H5O2 and C6H10O4. That's how you take the mass percent to the empirical formula and then take the next step to the molecular formula. You have to have an independently determined molar mass for the true compound in order to make that transition. And I can tell you how some of that's done, but I would be stealing my own thunder because in the second semester, we actually look at some of those methods. So come back for the second part. All right. Let's see. What's next? We haven't written a reaction yet and learned how to balance it. That's coming. Oh, by the way, I need to go get you those copies that I printed out. So let's take a break right here. If you need to go to the restroom, we'll come back in 5 or 6 minutes and pick up. Okay. We'll talk about this in just a minute or two. Balancing. Balancing equations. Let's see. 2 people sitting here? Yes. Okay. Throw me off. Wyatt never came in. Let's see. Nope. Wyatt didn't show up. I better check my roster. I know I lost 1. Maybe I lost Wyatt too. Let me see.
Was that him right sitting there?
He didn't sign
sign
in.
in.
Oh, he
He
didn't
was
sign
late.
in.
Yeah.
Oh,
I'm wondering.
see, if you don't sign in, I don't even know you're here. Yeah, you're right. That's why. Okay, I'm just gonna mark it present. Okay. That's good. I was afraid we lost another one. Okay. Give it a minute or two. Let's see. How much more do we have to do? Going to Ways to go. It's okay. We got time. Let's see. But Thursday, we don't have as much time, so if there's time left, I might get into chapter 4 a little bit, so we won't be squeezed on Thursday. Okay, still got another one coming. I need to bring a cup with me, stand these up on their ends. Make them last longer. Making sense so far? Okay, good. Just need to practice it. So you don't panic during exam. I don't know. Does anybody have test taking anxiety? Ooh, got a bunch. Okay. The way I got over test taking anxiety when I was a student was I tried to be over prepared. In other words, my goal was to know the material at least as well as the instructor, better if possible. I know that's a tall order, and I never really reached it, but working toward it, it saved my neck on exams. But I understand you might have other responsibilities pulling at your time. So try to maximize your efforts. And that's where working through the review document and treating it like an exam and then going back and checking it and find out where you're weak and working on those weak spots. That'll probably make your time spent more efficiently. And be sure you know the element symbols and how to name compounds. You have to know that. There's no two ways around it. I wish it was easier. Like we could put headphones on you. You could subliminally transfer information from a tape to your brain while you're sleeping, but our technology is not there yet. There was a movie, an old movie back, had Keanu Reeves was starring in it. He was Johnny Mnemonic. He had a port in his head, and he just plugged into the computer, and they loaded information in. Then when he got to his destination, they dumped it. And it created problems. Of course, otherwise it wouldn't be worth making a movie about, right? But we're not to that point yet. AI is not even close. AI is kind of it's good that they call it artificial intelligence because it's not intelligence. Well, we better get rolling. Okay, when we write a chemical reaction, this is how we construct our sentences. This sentence describes what happens during a chemical reaction in terms of reactants and products. And not only that, how many moles of each go into the reaction. So this example, I'm not going to write it on the board. C2H5OH is ethanol, right? That's the drinking kind. Plus oxygen. We initiate the reaction. You just need a ignition source, maybe a match or something, get it started, and it's self-propagating, and it will burn up all the ethanol with oxygen in the air and make carbon dioxide and water. Those are the products. And the way we write it, of course, left side is reactants, right side is products. And well, let's see, this is a 2-semester course. I will write it up here. H5OH plus oxygen yields carbon dioxide and water. I pick up the wrong one. Getting off a week. This is called a combustion. Whenever you combine something with oxygen and get products, that's a combustion. But notice I left out the why that happens. My mind's gone blank. These prefixes. God. Don't get old. We need these numbers here to balance the equation. Because if you count up the number of moles or number of atoms, either way, 2 carbons on this side, only 1 carbon on that side. Right. So this equation as written is not balanced. In order to balance it, coefficients. We need coefficients. A 3 here, a 2 there, and a 3 there. Now, if we count them up, 2 carbons, 2 carbons, 5, 6 hydrogens. 2 times 3 is 6 hydrogens. Oxygens, 6 plus 1 is 7. So 4 plus 3 is 7. Now it's balanced. We have exactly the same number of atoms on either side. And this arrow, for now, we just write the arrow from left to right. But we're going to find out eventually. We'll dig into it more in the second semester, but these reactions can run in reverse too. Now, they may be spontaneous in one direction and non-spontaneous in the other, but it's still possible. But for now, we'll just write the word left to right. That designates the left side as reactants, the right side as products. Oh, this whole slide's on balanced, so we know it's balanced. And you can talk about it in terms of number of atoms of each element or the number of moles of each element. Both of them work. Now, for doing our stoichiometry later, moles works better. So if you think of it in terms of moles, 1 mole of ethanol, 3 moles of oxygen gas gives 2 moles of carbon dioxide gas and 3 moles of water. Think of it in those terms, it's easier to calculate. This is, okay, that first statement is a qualification. The way we write these balanced equations, they're written with the assumption that the conversion is 100% efficient. In other words, you start off with this material and you end up with all of this and none of that. But like I said, the reaction can be incomplete, or you can get a reverse reaction that gives you some of your reactants. And the efficiencies, well, the efficiencies can be based upon that incomplete reaction or side reactions. Instead of going to this, it goes something else, or you recover it inefficiently. You try to capture the products and you got a leak somewhere. So as a practical matter, when you actually run the reaction in the lab, you're never going to get 100% efficiency. If you get more than 100% efficiency, then you're creating matter. It's more likely you're going to lose some. And we're going to deal with that at some point. When you write the first thing you do when you're going to write a sentence, a reaction, is you be sure you have the reactants and products written correctly. And you don't have coefficients yet. Okay. So if you know the products, you give them the products of carbon dioxide and water, and most of the time we give you reactants and products to write the reaction. There are a number of special cases where we can give you the reactants and you can deduce the products. but most of the time we give you both. And they may only be the names. Like we may only say ethanol plus oxygen yields carbon dioxide and water. And you have to be able to take that name and write the compound. If you can't write the compound, then you can't write the sentence. Okay. So ethanol, we would have to give you that one because we haven't discussed organic chemistry in here. The ethanol is, we would tell you ethanol is C2H5OH. But if we say oxygen, you know that oxygen gas is O2, not O. It's one of those diatomics. Not diatomics. So you have to know that. It's O2. Then carbon dioxide, you know that's a type 3 compound. 1 carbon, 2 oxygens. And water is standard of identity. And then you go to balance it. Once you've written your compounds correctly and put them in their proper place, then you go balance the equation. And that's why I gave you that handout. Now that's not a step-by-step how-to, but it does give you hints as to how to balance an equation. Right? Because what you're going to get from your textbook more than likely is balance by inspection. Right? Whoever writes these textbooks, at least most of them, not all of them. I think there's some coming now that actually give you methods for balancing equations. But at least when I was a student and for several decades, all they said was balance by inspection. So you're on your own, kid. The only condition is you have to have the same number of atoms of each element on both sides. Okay. So I've developed a method of my own for balancing equations. With these helpful hints. Now, we're not going to go through these helpful hints because I'm going to show you how to do it. Right. But they're there for you to read and go back and reference if you want. Let's see, helpful hints. Okay. All right, this includes helpful hints that I want to come back to. Let's see, I think the next slide. Let's go past the animations. Let's go to, let's go to this one. Or we could, I'll tell you what. Let's stop at this one right here. Okay, and let's balance this one. Let's find out how we got those coefficients in there. Okay. And to do this, I'm going to use what I call my budget method. So what you do is you write the compounds or the elements, whatever is on the reactants and product side. And then on this side, you say, I've got carbon in there. I've got hydrogen. I got oxygen. Does that cover everybody? Yeah, that's it. That's all the elements you have. And then you count them. What do you have to start with? Your beginning position. Well, we have 2 carbons. We have 6 hydrogens. We have 3 oxygens. On this side, we only have 1 carbon. And we have 2 hydrogens. And we have 3 oxygens, right? 3 oxygens? Yeah, 3 oxygens. Now this keeps a running tally of whether you got equal numbers on either side. Right now, you can see it's not balanced. So, question is, where do you start? Well, actually, let's take the flip side. Where do you don't start? You don't start with in single elements. If you've got a single element somewhere in that equation, you leave that element alone till last. Because when you put a coefficient in front of that element, it only changes that element. If you do it for any of the others, then it may change an element that you got to go back and fix somewhere else. So we keep this one till last. Okay. So we're not going to do oxygen, and obviously oxygen is already balanced. We're going to throw it out of balance in a minute. But for now, we leave it alone. If you can't figure out where to start, just start at the top. So we have 2 carbons here, we need 2 on this side. You get it by using a coefficient. That gives you 2 carbons here, and recalculate the oxygens. 5. Okay. Now we got our carbons balanced. Let's go to hydrogens. We've got 6 hydrogens on this side. We've got 2 on this side. If we put a 3 in front of that, we get 6 hydrogens, right? And we have 3 plus 4 is 7 oxygens. Okay. Now, how do we get 7 oxygens over here? Oxygens in 2 places. So if we leave this one alone, and we can make 6 oxygens out of this, then we can add that one and make 7. So if I put a 3 here, that makes 6 plus 1 is 7. Now you can see at a glance, we're balanced. That's my budget method. And I only had to use one hint or trick, is leave that one alone till last. All right. So now we can go to my animated one. All right. So here we have, it looks like a huge complex mess. But if you focus on what is on both sides of the equation, it becomes simpler. Right? You got ammonium complex ion on the left. You also have ammonium complex ion on the right. That's another one of my hints. If you have complex, if you have I need to take my ginkgo biloba, I guess. It's not complex ion, it's polyatomic ion, excuse me. NH4 plus is a polyatomic ion. It's on same on both sides, and it wasn't broken apart in the process. So we can use that as a balancing unit, right? That saves us a lot of work rather than breaking out the nitrogen and the hydrogen separate. If we use that unbroken polyatomic ion, then that saves us a lot of work. Phosphate is also the same on both sides. So we have ammonium, phosphate, calcium, and chlorine. Right? That's all the balancing units in that equation. Then we do our initial tally. On the left-hand side, we have 3 ammoniums, right? The subscript of 3. We have 1 phosphate, we have 1 calcium, and 2 chlorines. Then we tally on the other side. We have 1 ammonium in the ammonium chloride. We have 2 phosphates. We have 3 calciums and 1 chloride. Now, we don't have any single elements, so there's nothing to hold out to the end. What we have to decide is, what's the most efficient way to start? Usually, if you start anywhere, you'll eventually get to the end, as long as you don't make any mistakes. But sometimes you can start with experience. You know that starting in one place will get you there quicker than another. And in this case, I started with calcium. Right? We got 3 calcium on the right. I'm going to put a 3 in front. That's what that little red says. That's the first step I took. Right? And you'll see, it might be difficult in the review document for balancing equations. Yeah, they're all black and white. Oh, but I do. You can see that I have 1s, 2s, and 3s in little circles. That tells you the step, right? If I just put up the balancing equation right there, then you wouldn't know which step I took first. So that's why I put those 1, 2s, and 3s in there, like I'm doing here. So that balances the we recalculate the calcium, and that we have to recalculate the chlorines also. Okay. So now we have 3 calcium, 6 chlorine. I'm going to go on the right-hand side and balance the chlorines now. So I put a 2. Remember, you can only balance with coefficients. Can't change the subscripts, right? They're chiseled in stone. So we put a 6 in front. That gives us 6 chlorines, which balances the chlorines. But it also changes the ammonia. And I did the ammoniums first, so there we go. So now we have 6 ammonia on the right. We only got 3 on the left. So how do I get 6 ammoniums on the left? I use a coefficient of 2. Right? A 2 times the subscript of 3 on the ammonium gives me 6 ammoniums. Okay. And then recalculate the phosphates with the 2. And that gives me 2 phosphates. And now you can see 6, 2, 3, 6. We're balanced. Okay. What we try for when we're balancing equations is the simplest whole number ratio of coefficients. Now, if you don't have a number in front of the compound or the element, what does that mean? That means it's 1. Because if you write it there, there's got to be at least one of them. We just don't write the 1 in because that's redundant. So CaO2 plus 3C yields CaC2 plus CO2. Is that correct? Well, no, because CaO2 is not a correct compound. So it can't be number 1. But if we multiply the balanced equation, actually, if we balance the equation, the simplest numbers, we get 2 calcium oxide plus 5 carbons yields 2 calcium carbide plus carbon dioxide. But technically, we could say divide by 2 and get that one, divide everything by 2, or we can multiply by 2 and get that one. Right? So they would still give you the same ratios, but to standardize our whole procedures, we try for the simplest whole number ratio. So the last thing you should do when you got a balanced equation is look at the coefficients. Can you divide by 2 or 3 or 4 and simplify them? If you can't, then that's the end. You stop there. We prefer the Roman numeral 2. Okay. So this is just a check to see if you haven't picked up any misconceptions. Which one of these is true? The number of molecules is conserved. No. If you add up the coefficients, that tells you the number of molecules on one side versus the other, and they don't necessarily match. If they do, it's coincidence. The coefficients tell you how much mass of each substance you have. No. It tells you how many moles of each substance you have. If you want to know how much mass, then you got to take the number of moles times its molar mass. That'll tell you the mass if you have that many moles. Atoms are neither created nor destroyed. Good to go. Right? That's Dalton's atomic theory. Okay. Coefficients indicate the mass ratios. No, that's another way of saying number 2. Sum of the coefficients on the reactant side equals the sum of the coefficients on the product side. That's another way of saying number 1. So the only one out of that whole bunch that's true is number 3. Let's see. Number of atoms has to be the same on both sides of each element, that is. Not the total atoms, but the number of elements of each atoms of each element, or the number of moles of each element must be the same on both sides. You can't change the subscripts of a properly written compound. Right? That's cheating. A balanced equation tells us the ratio of the number of molecules which react and are produced in a chemical reaction. Yes. Those coefficients tell you how many molecules of this plus that number of molecules yields this number and that number. And that's only if you have 2 and 2. I mean, you could have 1 on this side and 5 on that side. And hopefully at some point I'll show you one of those, the decomposition of nitroglycerin. It produces lots of gaseous products. That's how it gets its explosive force. Coefficients can be fractions, but for now they should be given as lowest integer multiples. Yes. We will come to a point where we have to use fractions because of what we're trying to accomplish with the equation, right? But we're not there yet. Okay, when we do stoichiometric calculations, we're trying to relate the mass of reactants to the mass of products, but we can't do it directly because a balanced equation does not represent masses. It represents numbers. So I'm going to give you a method for making the conversions and determining the stoichiometry of a reaction. If you're given certain mass of reactants, you can calculate what to be expected with 100% efficiency of products. And the magic number in there is molar mass. All right. So we're going to balance the equations just like we did before. We have to convert all the masses into moles before we can go anywhere in the equation. You can't move anywhere if you're mass, you're stuck. And then we use our conversion factor from moles of one reactant to moles of product are the coefficients. I'll show you how this works. And then once you've got the number of moles of product, you can convert back into mass using the molar mass of the product. We need an example, I think. There's a flow chart if you want to use it, that's fine. How about this one? Let's say we have P4 is a solid. Well, that's not working. Let's grab another. P4 is a solid. The state of the reactants and products isn't always necessary, but it's a good habit to get into because at some point you're going to have to know the state in order to complete a reaction. That's a gas, excuse me, gas. This makes P2O5. Yep. In this case, in this case, the creator of the slide balanced the equation for us. And you can check it just to be sure. Like 4 phosphorus, yeah, 2 times 2. And 10 oxygen, 5 times 2. Yeah, it's balanced. So we read from the problem that we have 6.25 grams of phosphorus. 6.25 grams of phosphorus is burned. What mass of oxygen does it combine with? How much oxygen is required? So this is what we're headed for. We want to know the grams of oxygen. Well, like the rules say, if you're grams, you're stuck. You can't move anywhere in that equation. In order to get over or under that wall, you've got to convert to moles. So we need 6.25 grams of phosphorus converted to moles of phosphorus. Oops. There. So 4 times phosphorus, 30.97. Would give us the molar mass of P4. Now, P4 is still an element, right? It's an allotrope of the elements. There are various forms of phosphorus. You've heard of white phosphorus and red phosphorus, right? What is it? White phosphorus is more reactive, I think. You have to keep it submerged in. Is it water or oil or the other? Keep it away from air. But 4 times that is 123.88. So 123.88 grams divided into this many grams of phosphorus will give us the moles of phosphorus. Then we can move. So I'm gonna put 6.25 and flip them and divide. Here we go. This is 5.05 times 10 to the minus 2 moles of P4. Now, how do we get from moles here to moles there? We use coefficients. Right? The ratio of moles of P4 to moles of oxygen is for every 1 P4, you need 5 oxygens. That's your conversion factor. Okay, that cancels moles of P4 and leaves you with moles of oxygen. So I just need to multiply 5 times that. And that's 2.52 times 10 to the minus 1. 2.52 times 10 to the minus 1 moles of O2. We're almost there. Questions? Okay. Now we need to convert oxygen back into grams. 2.52 times 10 to the minus 1 moles of oxygen. We need a conversion factor that converts moles into grams. And oxygen is 32 grams per mole. So 32 times that, the moles cancels, leaves us with grams. 32. So that's 8.07. So 8 grams of oxygen is required to burn 6.25 grams of P4. Okay. Let's see. Yeah, we just have the answer. That's how we got the answer. So we go grams to moles, moles here to moles here, then moles back to grams. That's how you have to do it. And that's going to be the pattern for determining outcomes for reactions. Now we could have gone over this way and say, once we have moles of this, we can find out how many moles of that and convert it back into grams. Right? Once we have moles, we can move anywhere. It would take a different conversion factor and then a different molar mass. But we could do it if the question asked for it. Okay, I'm gonna leave that there just in case. Okay, this is different. Now this method, we're starting off with convert grams to moles, then moles to moles, and then moles back to grams. That's our starting point. But that's for solid and gas reaction. If you have, say, 2 solutions where you have different concentrations of reactants, then you need to use some other method to find out how many moles of the reactant are actually involved in the reaction. But it's still whatever you have to moles, and then back to what you want. Right. In our case, it was mass that we wanted, but you could come back to concentration in solution, or you could come back to mass for all that matter. But it's a similar pattern. You got to get to moles before you can move. All right, this one is a little complex. I'm gonna try to make it understandable. We've got 2 reactions here, 2 separate reactions. Methane reacts with oxygen. Methane, did I tell you what? Yeah, methane is CH4. Methane is a gas, normally, you know, unless you're inside one of Elon Musk's rockets, and then it's a liquid. I think they call it methalox, that type of rocket. Plus oxygen yields carbon dioxide and water. Yep. CO2 gas, and water. Doesn't say whether it's, actually, it doesn't matter if it's a gas or a liquid at this point. Excuse me. If we're holding things, everything at standard temperature and pressure, standard temperature is, let's see, for most reactions is 25 degrees Celsius, and pressure is 1 atmosphere. Then this will be a liquid. But if we're letting the reaction run and all the heat build up, then this is still going to be a vapor. So it doesn't matter really. And the other equation is we're going to burn ammonia gas plus O2. And that produces nitrogen monoxide in water. This is one where I could conceive, well, for either one, I could conceive of side reactions that give you the wrong products. Right? This could give you carbon monoxide instead. Or this could give you NO2, for instance. Those are possibilities for decreasing your efficiency. But for now, we're going to assume that it's 100% efficient to these products and these products. Now, write the balanced equations for each of these reactions. So we could do our budget. And some reactions, they balance so easily, you don't even need the budget. But for now, we need practice, right? We need practice doing the budget. So we need carbon, hydrogen, oxygen. We got 1 carbon, 4 hydrogens, and 2 oxygens. On this side, we got 1 carbon, we got 2 hydrogens, and 3 oxygens. Okay. We're not going to mess with the oxygens, and the carbons are already balanced, so we'll do the hydrogens first. So we need 4 hydrogens. It's only in one place, so 2 in front gives you 4. And then 2 times 1 is 2, plus 2 is 4 oxygens. Okay. Then all we need is 2 here, and that gives us 4. So that equation is now balanced. Erase this, because we're going to need room for calculations. Now we need to balance this one. So we'll use our method, nitrogen, hydrogen, oxygen. 1 nitrogen, 3 hydrogens, 2 oxygens. On this side, we have 1 nitrogen, we have hydrogens, 2 hydrogens, and 2 oxygens. Okay. We're going to leave oxygen till last. So let's look. Hydrogen is our only candidate now. So here's the problem. You got 3 hydrogens in one location here and 2 hydrogens in one location there. There's another hint in that document. And look for the term cross multiply. If we take this 3 over here and that 2 over here, that gives us 6 hydrogen here and 6 hydrogen there. Then we have to reconcile the others. So that's 2 nitrogens here. And what we did over here was give us 4 oxygens, correct? Yep. Okay. Now we need 2 nitrogens on this side. That messes up our oxygens. 2 plus 3 is 5. 5 oxygens, right? Okay. Time for another trick. At the end of a balanced equation, you want whole number coefficients. But there's nothing that says you can't use fractions in the intermediate, to accomplish your mission. In that case, I need 5 oxygens on this side. Right? I got 5 over there. I need 5 over here. Well, How do I get 5 oxygens out of an O2? If I say 5 halves times 2 is 5, isn't it? It's like saying 1, 2, 3, 4, 5. There we go, there we go, there we go, there we go. Okay, there's the 5 O2s, but I want to take half of each one. So that's only 1 of each. There's 5. Okay. So that's an intermediate step. I want whole numbers. So once you've got, this is balanced, right? Now we have 5 here. That's a balanced equation. But we want whole numbers. So how do you get whole numbers out of that? You got to get rid of the fraction. So that means you've got to multiply the entire equation through by some factor that gets rid of that fraction. So if we multiply everything through by 2, that'll get rid of this fraction. 2 times 5 halves is 5, correct? 2 times 2 is 4. 2 times 2 is 4. And 2 times 3 is 6. We've used our 2. So let's clean this up. There's a 4. There's a 5. There's another 4. And there's a 6. Okay. So now we have 2 balanced equations. That answers that first question. Let's see, go to the next. There it is. Okay. Now, what's the next question? Once we got our balanced equations, we got these 2 different reactions, but we're going to relate them to one another through comparing the amount of water they produce. Okay. So what mass of ammonia would we produce? What mass of ammonia would produce the same amount of water as 1 gram of methane? So we want these 2 to be equal in mass, right? Since they're the same formulas, moles would be equal also, right? So if we find out from here, how many moles of water can we produce? Then we say that's the same number of moles here. And then we work our way back from that moles to this grams, and that tells us how much ammonia in mass is required to produce the same amount of water for this reaction as for that reaction. That's the bird's eye view. Okay, so we go that direction, but we're stuck unless we do what? Change to moles. So we need a conversion factor for methane. Grams and moles as quotients means molar mass. So 12.01 and 4.04 for the hydrogens. 506, 1605. Tells us how many moles of methane we're starting with. That's a bad habit. Ending sentences with prepositions. Let's see, this is 6.23 times 10 to the minus 2 moles of methane. Let me clean this out here. Okay. Now we want to convert methane into moles of water. Right. So what's the ratio of methane to water? Well, 1 methane is 2 waters. So I just have to multiply by 2. 1.25 times 10 to the minus 1. 10 to the minus 1 moles of water. Okay. That's the same amount of water as we're going to have here. Exactly. But that's what the problem tells us it is. So I'm going to work backwards now times 10 to the minus 1 moles of water. And then I'm going to need a conversion factor that'll give me cancel moles of water and give me ammonia. So the conversion factor now is 6 and 4, or 2/3. And that will give me moles of ammonia. Yeah, I'm working backwards. 4 times and 6 divide. This is 8.31 times 10 to the minus 2 moles of ammonia. Okay. Now I want to convert to grams. So I need moles on the bottom. This is in the numerator. This is in the denominator. So I need the molar mass of ammonia. 14.01 and 3.03 for the hydrogens. 1704. So 17.04 times that is 1.42 grams of ammonia. That's how much ammonia we have to burn to give you the same amount of water as 1 gram of methane. Okay. There we go. Okay. That gives us, okay, that's standard notation. So they're going out to 4 decimal places. So we might be off a little bit. And there we have same number of moles of water, convert to moles of ammonia, then convert to grams. So, okay. We must have the same error. End up with the same number. We're in agreement. Okay. I know that was a complex problem, but it's an example of the type of problem that is multi-step. So you have to logically break it into pieces. Okay. That's why the instructions in his slides took you through each step. Balance the equation first. Right. Then take the premise. 1 gram equals what? Water. And then that amount of water is equal to the other one. And then you work your way around. Okay, now we're going to talk about limiting reactants. Before we talk about efficiencies, we're going to talk about limiting reactants. So let's see, should I be erasing that? Yeah, that's fine. It's a different reaction. What do you think limiting reactant means? It means more than just another headache on an exam. It means money to any chemical engineer that's working for a company. You have to know how much of each reactant goes into the reaction vessel. And then the next step is the efficiency. How much can you expect to come out of the reaction? Limiting reactant is the first place to start because the limiting reactant, when you have 2 or more reactions on the reactant side, it's if both, say you only have 2, if both of them are completely used up and you make product, that's 100% efficient conversion. Plus, since there's nothing left, you have exactly what we call stoichiometric ratios. Exactly the right amount of each one to give you only products and use up all the reactants. In the real world, that never happens, ever, because of experimental error, measurement error. You can never measure exactly the right amount of reactants so that you use both of them up. Experimental error, measurement error, is going to dictate that one of them will run out first. Now, it's possible that you're trying to reach a stoichiometric ratio. In that case, you don't know which one's going to run out first because you didn't set it up that way. But if you set up your reaction so that you know one of them is in excess and the reaction is limited by the other reactant, that's the limiting reactant. When it's used up, you'll have some of the other left over, the excess, and you know the reaction will stop then. Okay, so here's a stoichiometric mixture for the Haber-Bosch equation. N2 plus H3 yields ammonia. They're all gases. Gas, gas, gas. And we need 2 here and oops. Never saw that molecule before. H3. Maybe in the upper atmosphere, I don't know. But the stoichiometric ratio would be for every 1 nitrogen molecule, 3 hydrogen molecules come together to make 2 ammonias. So if you look the way they've got those red dotted lines around there, the blue ones are nitrogen and the white ones are hydrogen. So the ratio there is 3 hydrogens for every 1 nitrogen. That's a stoichiometric ratio. And if it's stoichiometric, then you come out with only 2 ammonias for every one inside every one of those red boundaries. Okay, that's the one that never happens. By the way, this equation is famous in most circles. Fritz Haber was a German chemist who was working in the early 20th century. And he was trying to find a way to manufacture nitrates. This was one step on the way to nitrates. If you take ammonia and react it with oxygen, you get nitrates. And when you've got nitrates, you can make explosives. So he was trying to make explosives for the German government because before World War I started, the Allied nations were boycotting Germany and their access to bird guano, mostly on the coast of Chile, which is like meters thick. And you just mine it and make gunpowder out of it. But Fritz Haber was a good German citizen. He's a patriotic person, and he developed this procedure for making ammonia. They knew that once they had ammonia, they could make nitrates, all day long. So he worked out the chemistry behind that, and it wasn't an easy task, but he managed to do it. And then Haber came along and stepped it up to industrial production and made it more efficient, stepped it up to making it in mass quantities, so to speak. Okay. Limiting reactant. This is an example of a limiting reactant. In this case, which one's limiting? Well, which one? Actually, the easiest way to determine limiting is to determine which one's excess. In this case, nitrogen's excess because you've got 2 unpaired and they're still on the other side. So nitrogen's excess, that means hydrogen has to be limiting. It runs out first. Okay. Let's see. How are we doing? 3 o'clock. Okay, we have 50 minutes. I may not get to the chapter 5 of chapter 4 today. Which means probably on Thursday, I'll run over. Which is okay. I mean, you need time to digest this, don't you? So if we have this equation where we're taking hydrogen and reacting it with oxygen, make water. And let's see, we have 2 of these. Yeah, that's right. And some rocket engines operate with these type of reactants: liquid hydrogen, liquid oxygen. That's what the space shuttle used in its main engines. And then, of course, they strapped 2 solid rocket boosters on the side because those 3 main engines weren't big enough. They couldn't do the job. So they tried to launch in too cold weather, and the O-rings blew out. and they burned a hole in the big orange tank. And after that, we created 6 angels. Astronauts bit the dust. Anyway, so this ratio, if you have if you have 2 moles of hydrogen and 2 moles of oxygen, how many moles of water will you produce? If you have 2 here and 2 here, the limiting one is this one, because you only need 1 of these to make the reaction go, and you're going to have 1 left over. So you should have you should have 2 moles of water produced from that first one. Oops, I gave away the answer. How about the next one? If you have 2 and 3, you're still in the same situation. Only have more oxygen left over, but you still only make 2 moles of water because that's the limiting one. If you have 2 and 1, 2 and 1, that's stoichiometric, 1 and 2. The third one, 3 and 1. If you have 3 here and 1 here, now oxygen is limiting. And 1 of these makes 2 of those, with 1 of these left over. You've used up 2 of them. Now you got 1 left over. And then the last one is the answer. All of them make exactly the same amount of product. Only from a practical standpoint, you got to separate the unused reactant from your product. If you only want water, then you got to separate out the excess somehow. With gases, it's not that difficult. Let's see. So you can't simply add the total moles of all the reactants to decide which reactant mixture makes the most product. Right. From a practical standpoint, you have to think about how much product can be formed from each of the reactants. So if we have let's say we're not arguing from the standpoint that we were before. In other words, we're saying if we've got 2 and 2 here, how much water can 2 of these make? It can make 2 of those. What if we have enough hydrogen? How much can this make? 2 of these can make 4 waters, can't they? So this is based upon hydrogen, and this is based upon oxygen. Well, what you do is say, which one makes the least amount? Hydrogen. Hydrogen's limiting. Okay, that's the approach from a practical standpoint from any other problem that you're given. If you're given 2 absolute amounts of 2 reactants, then you can be pretty sure that one of them is going to run out. One of them is limiting. Okay, percent yield. This is the way that chemical engineers deal with keeping their bosses happy. You want as high a percent yield as possible. You want to approach 100% if you can get it, because that means money. So you need to know what the percent yield is. So what the calculation is, what's the actual yield? The actual yield that's measured from a test reaction. And then what's the theoretical yield based upon the stoichiometry of your balanced equation? That ratio times 100 equals percent. Now, it could be mass to mass. It could be volume to volume. It could be moles to moles. You have to be told what it is. All right, so let's take an example. this the last one? Yeah, this is the last slide. Okay. So we can take our time and absorb. All right, in this case, we've got some more P4, but this time we're going to react it with fluorine. And believe me, this is going to be a very energetic reaction, exothermic. So we want to conduct this in a safe environment. 6F2 gas yields PF3. And this is also a gas. Okay. The question is, what mass of P4 is needed to produce 85 grams of PF3? So we want an output of 85 grams of that product, but it's not 100% efficient. We're told that the efficiency is 64.9% efficient. Okay. Okay. So since these equations are theoretical 100% efficiency, you've got to find out what value would be here with this efficiency to give you that amount. Okay. Then you can work backwards, but you have to find out what this one is first. Okay. If 85 grams is what we're expecting, and the efficiency is 64.9 grams actual per 100 grams theoretical, this is actual, right? We want theoretical, 100 grams theoretical from 64.9 grams actual, right? So that's the way you would lay it out. To understand what's being canceled, what you're left with, but once you get comfortable with it, you can just say 85 divided by 0.649, and you're off to the races. Get the same result. Okay, so this is going to tell us what the theoretical amount needs to be to give us the actual amount. Let's see, 85 divided by 64.9 times 100. 130.97. 30.97 grams. That's what goes here. Okay, that's the theoretical. Now we can work our way back. And I kept extra decimals just to avoid rounding error. 130.97 grams of PF3. We want to convert to moles because we can't go anywhere without moles. We need phosphorus is 30.97 and fluorine is 19 times 3. So that's 87.97. So 87.97 grams per mole divided into 130.97. And I get 1.489 moles of PF3. Now we can convert it to moles of P4. Right? And the conversion factor is derived from the coefficients. That cancels this one. So this one is 4, and that one is 1. So we just divide that by 4, take a quarter of it. 0.372, 0.372 moles of P4. Now that we have 0.372 moles of P4, we need the molar mass of P4. Right? So that's 30.97 times 4. Is 123.88. Yep. So that's times 0.372. And I get rounded off 46.1 grams of P4. That's what you need to give you theoretical with efficiency to give you actual 85 grams. Okay, there's the animation. Oh, here we go. And there. 46.1 grams is required for that reaction with that given efficiency. That's pretty high efficiency, actually. Haber, when he first started with his efficiency was less than 1%. And he worked on it. He changed the reaction conditions, he added a catalyst, and he got it up, and he recirculated, constantly recirculated, and got it up to 15%. And that was industrially useful. He circulated it, actually, you've got 3 gases there. You got nitrogen, hydrogen, ammonia. Ammonia will condense at a much higher temperature than nitrogen and hydrogen. Okay, so all he had to do was bleed some off, cool it down, ammonia drained off, and he took the other gases and fed them back through, and just kept doing that, cycling over and over. After about 4 or 5 cycles, he got up to 15%, actually a little higher. So there's more than one way to skin a possum. I don't skin cats. They're my friends. Okay, any questions? Practice, practice.